Okay, we are going to start a chapter. We're going to be doing a couple sections in it, but to introduce you to what we call conic sections. And as you read in the book, the intersection of any double cone and a plane is called a conic section. And then we will show you some diagrams here that show how the different conic sections come about. So we're talking about circles, ellipses, parabolas, and hyperbolas are the ones we're most familiar with. So let's take a look. Our goals today will be to classify a conic section as the intersection of a plane and a double cone, which was the definition you've already read about. And we want to also use the distance and midpoint formulas to help us find some other combinations, which you will see or hear me talk about in our work. All right, so here is a good illustration of a double cone and the different ways that a plane can intersect that double cone. So if you look carefully, and I'm sure you could find plenty of little short videos about this that are probably interactive, but you will notice that in this first one, in your double cone, the plane intersects only one of the cones, and it is parallel to the base of the cone. Think of it that way. So if it is parallel to the base of the cone, the part where the plane and the double cone intersect is that red circle. Versus if you take the plane and you put it on some sort of angle. And as long as that angle is less than the angle made with the intersection of the two cones. If you do that and it intersects your plane in this double cone, you will get an ellipse. So two of our choices. If the plane is parallel to the base, it's a circle. If the plane is at some angle that is less than the angle of intersection of those two cones, you would get an ellipse. Then take a look. If your double cone is intersected with a plane that is on the same angle, so notice as you look at your work here, here is what we're talking about, the angle of those cones. So your plane is intersecting on that same angle. So it's sort of like parallel to the cone. So if the plane is parallel to the angle made by the double cone, then you will get that red portion that represented your parabola. So we've got a circle, we've got an ellipse, and we've got a parabola with our plane. What else could we do with that plane? Well, we could make that plane run perpendicular to the cone, or say that it intersects the cone at 90 degrees. And so with the base, and if you do, you see we are getting a double portion. Unlike the other two, you only had an intersection in one half of the cone. Here we're getting a double portion, and we call that a hyperbola. And we've seen that and graphed it on a two-dimensional plane. Now here's what it looks like in a three-dimensional lookup. So my question here is, and why is this section that we're studying called conic sections? Because an intersection of a double cone and a plane is called a conic section. So a double cone and a plane. So you're being a little more 3D. You got to be out there thinking, okay, visual. So knowing that, we're going to give you some equations, and we want you to graph the equation and identify the conic section. So now, of course, we're going back to, we are going to be graphing in 2 dimensions, which is what we have been doing. So if we give you an equation, you might not recognize any of the equations. X squared plus y squared equals 16. If we do that, x squared plus y squared equals 16, you should be able to tell me, hey, in order to graph, I know I need y by itself. So what have we done in the past? We've moved the variables. So let's move that x squared over to the other side. make it negative, we now have a y squared. So y squared needs to be rooted, square rooted. And when we do that, we get the equation y equals plus or minus the square root of 16 minus x squared. Now, you should be able to go to your grapher. So let's grab that now and do that. Now, going to your grapher, you're going to have to be careful. You cannot put in the plus minus that we had. So notice how I have it separated into two equations. One that's plus, one that's minus. And then when you graph, notice in red I have the plus version, in purple or a bluish color I have the minus version. That whole combination is actually the graph. So then when you look at it here, what do we have? You should be able to say we have a circle. And so identify it, finish with a circle. Okay. Next, same thing. Different equation, few more numbers, etc. in it. So graph the equation and identify this conic section. So we'll start the same way. We want to get our y squared, our y value by itself for graphing. So first, let's move the 9x over. Divide by the 16. When we do, we'd have a y squared equals 144 minus 9x squared. But to get rid of that 16, or sorry, to get rid of the y squared, we would have to take the square root of both sides. So we're looking at plus and minus the square root of 144 minus 9x squared, all divided by 4. So again, be careful here. Going to our graph this time, there's our two equations, broken up, all under the square root. We don't have that circular effect that we saw last time. Again, my top half of my equation was the red portion, the bottom half was the purple shape. I don't believe we want to call this one a circle. So of our choices there, I think we're going to be saying we've got an ellipse this time. So you can start noticing some characteristics in your equations. Both that circle equation and that ellipse equation were very similar, but they had some distinct differences. And our goal right now isn't to memorize their equations. We'll get to those as we go, but to look at the differences and subtleties, I guess it would be, in those equations that make them. Because ellipses and circles were very similar when you talk about that conic section. It is a plane that intersects only one of the two cones, and it's how are we putting that? The ellipse was any angle not equal to the angle of the two cones, but the circle had to be parallel with the base. So start noticing, as we said, some characteristics of the equations, because that'll help as you go along, and so you can start recognizing, oh, that's a circle, that's an ellipse, that's a parabola, that's hyperbola. Okay? Next, we want to review a couple formulas, and so they're here. Your distance formula definitely should be memorized by now, and your midpoint formula should also be memorized by now, because you're going to see in this section several examples. Here is one. Find the distance between these 2 points. You can do that. You can do it as an exact answer, and if it doesn't come out exactly messy, you can round to the nearest hundredth, tenth, whatever's called for. Another type of question you might have, find the coordinates of the midpoint of the line segment whose endpoints are at this point and this point. So you would definitely need the midpoint formula for that. And then here's a third one. The endpoints of the diameter of a circle have the coordinates 4, -3, and -1, 9. If I give you that much information, using your midpoint and distance formula and maybe some other formulas about a circle, you should be able to find the center, find the circumference, and find the area of that circle. So basically, once I give you the 2 points, your job is to find how big it is. And you have several ways you can do that. And then you've got your circumference formula, area formula, things like that. So those are the type of problems we're going to have today. Our graphs, so that we get to see the different conic sections in 2-dimensional graphing, and then also some geometry style questions using the distance formula, midpoint formula, and maybe some of your circle formulas as well. So you should be good to go. Giving you a little look at how the graphs worked, but I think you'll be fine.